Hey guys, welcome back. So if you watched the previous video, we looked at the ways you can kind of travel through a network from different vertices along different edges and the different categorizations that we call them. Last lesson we looked at, or last video I should say, we looked at trails, which is a type of walk where you don't repeat any edges, but you're allowed to repeat the vertices. Okay, so you don't repeat any edges, but you're allowed to repeat the vertices. Now, an Euler trail is just a special type of trail named after Leonhard Euler, who was basically this genius who came up with all these groundbreaking ideas in maths. And a lot of the kind of inventions that he came up with we still use today. But specifically on this, an Euler trail basically is a network that uses every edge only once. So, Euler trail is a walk that uses every edge exactly once. If it starts and finishes at the same vertex, like we learned last lesson, it will be a closed trail. And what do we call a closed trail? Well, we call a closed trail a circuit. So if it uses every edge exactly once and starts and finishes at the same place, it must be called an Euler circuit. But we'll talk about that a bit more in a second. Now, as you can see, this decision table, although it simplifies things a bit, it is starting to get a bit complicated. But lucky for us, there is a simple way to find out whether or not a network has an Euler trail. So the first one is, if an Euler trail exists, that network must have exactly two odd vertices. Okay, exactly two odd vertices. That's simple enough. Now that's nice because it tells us that we don't need to guess and check, and we don't need to go through exactly every single test to find out whether or not something is an Euler trail. We just got to see if there are exactly two odd vertices. So let's have a look at this example down here. So does each network have a Eulerian trail? So first things first, let's label the degrees in the network. So remember, degrees are just how many edges connected to the vertices. So for A, that would be 2, E would be 2, B is going to have 1, 2, 3, C is going to have 1, 2, 3, and D is going to have 2. So you can see here you've got exactly two odd vertices. So this is going to be a yes. Let's look at B. So how many edges connected to X? That's 3. How many edges connected to T? That's also 3. M is 3 and W is 3 also. So this one's going to be no because there's not exactly two edges, exactly two vertices that have an odd degree because they've all got odd degrees. So that is a no. Okay, let's look at C. All right, how many edges connected to G here? 1, 2, 3. How many connected to N? I got 1, 2, 3. How many connected to M? 1, 2, 3. L is 2. K is 1, 2, 3, 4. And H is 1, 2, 3. So here, once again, this won't be 1 because we don't have exactly two odd vertices. Now let's look at Euler circuits. So Euler circuits have a slightly different way to find out. An Euler circuit must have all even degree vertices for it to exist. So remember, it just means closed. So it starts and stops at the same place for an Euler circuit and uses every edge once. So once again, we're going to kind of test all the edges. So let's look at A. So what's the degree of A? 1, 2, 3, 4. What's the degree of B? That's 2. What's the degree of D? That's also 2. What's the degree of C? So 1, 2, 3, 4. And E is 2. Okay, so this is going to be a yes because all vertices have an even degree. Now let's just test this out. Does this in fact have an Euler circuit? So do we use every edge exactly once? And do we start and finish at the same place? So let's say I start at A, I come down to C, I go to B, I go to A, I come back down to C, go to D, I go to E, and I go to A, so yes. So I've used every edge exactly once, and I've started and finished at the same location. All right. B, so how many connected to vertex F? So it's 1, 2, 3, 4. How many connected to E? That's 1, 2, 3. How many connected to D? So it's 1, 2, and 3. How many connected to C? That's 1, 2, 3, 4. And B is 2. So this one is no, because not all the vertices have an even degree. In fact, there are exactly 2 odd vertices. So that's going to be an Euler trail, this one here. So last one, C, how many connected to W? So that's 1, 2, 3. How many connected to K? 1, 2, 3. How many connected to Y? 1, 2, 3. How many connected to B? 1, 2, 3. So once again, this is going to be no, because they're all odd degree vertices. Okay, let's look at one more example here. So does the network below have an Eulerian trail or an Eulerian circuit, or neither? So you must give reasons. So once again, here you have a weighted network. Now we're going to label the degrees. So A has degree 2, B has 1, 2, 3, 4, D has 1, 2, 3, E has 2, F has 1, 2, 3, and C has 1, 2, 3, 4. All right, so what do we notice? Well, actually, we've got exactly 2 odd vertices. So what does that mean? That means when we have exactly 2 odd vertices, we've got a Eulerian trail. So let's test that. So remember, it has to start and finish, it has to start at one of the odd vertices. So let's have a look. And we're going to use every edge once. So D to E, E to C, C to F, F to B, B to C, C to A to B. Oh, I've gone the wrong way. Let's try that again. D to E, to C, to F, to B, to C, to A, to B, to D, to F. Oh no, I had it. Okay, so remember, we can repeat a vertice. So that would be an Eulerian trail, exactly 2 odd vertices. All right, cool. So I hope that makes sense to you. If you have any questions, let me know down in the comments below, or if there's any other videos you'd like to see, hit me up. Otherwise, I'll see you in the next one. Thanks.